in the cluster should be very large. So because cluster is the place where the most surprisingly large amount of dark matter is concentrated on, this is the perfect place to study about the dark matter. And also, they have a large population of the galaxies, which can be used as a direct probe of the dark matter properties. So that's the reason why we need to study galaxy clusters. Clusters can also be the cosmological tool, especially the mass functions of the clusters can be a totally independent tool for studying cosmology compared to the CMBs or large-scale structures and so on. So that's why we need to study galaxy clusters. Let's take a look at the image of the galaxy cluster. This one is a cluster at ratio 0.008. It's actually 0.08. It's a cluster called Abell 2029. The central galaxy of this cluster is known as the biggest galaxy in the local universe. There are three ingredients to study galaxy clusters. First is the dark matter. Dark matter possesses about 80%, more than 80% of the mass of the galaxy clusters. But as name implied, it is really hard to probe dark matter with the observational directly. But these days, with lensing has been a tool to trace the dark matter distribution of the galaxy clusters. And this map shows the dark matter map traced by the weak lensing techniques for Abell 2029. So there is a very central mass concentration at the center of the cluster, and there are several substructures which shows the concentration of the dark matter. The second ingredient is the intracluster medium. Intracluster medium possesses about 10 to 15% of the cluster mass. They are extremely hot, so we can trace the intracluster medium based on the X-ray emission. So from the extended X-ray emission, we can study the details of the intracluster medium distributions of the galaxy cluster. And this is also the X-ray imaging of the Abell 2029, the cluster we saw just before. And these intracluster medium shows the very similar structure with the dark matter, which means there are indeed strong mass concentration of the dark matter, which attracts the intracluster medium. And then they emit the strong amount of X-ray emissions. The final ingredient is the galaxies. This map shows the background color density map shows the photometric galaxy density maps, and the contour shows the density map of the spectroscopically confirmed galaxies. And it shows also the central concentration, as you saw in the dark matter and the X-ray map, and the surrounding substructures. With these galaxies, we can investigate how these galaxies are moving along around the galaxy clusters with the interaction with the dark matter and the intracluster medium. One thing that we notice here is this structure is not appeared as a cluster members. So dark matter, X-ray, they only give us some information in the line of sight direction. Once we have very dense spectroscopy like this, we can have three-dimensional structure of the system, which will give us more chance to understand the details of the galaxy systems. There are also the other tools that we can use to study galaxy clusters. Observational data, of course, is widely used. And today I'm going to focus on the spectroscopy observations of galaxy clusters. And the numerical simulations has been much easier to analyze these days. So I think especially IllustrisTNG people make everything gets very easy, make it very easier. So even an observer like me can analyze the simulational data without a huge amount of difficulties. So I have a quick question for you. So I'm showing two images of galaxy clusters. And which one do you think comes from the observation? And which one comes from the simulation? Who think the left image comes from the observation? who think the opposite? Okay. Jun Sung-ho I know very well, who's a theorist. Of course, think this one is from the simulation. Indeed, this one is from the observation, this one is from the simulation. So the question I had was how to connect these two. The system we found in the observation, and if we want to get some theoretical guidance to understand the formation and evolution of this kind of system, observed system, we want to find the similarly looking system in the simulation, and how to find them, how can we connect them with the observation. That is the fundamental question I have. The cosmological simulations are becoming a very useful tool for the cluster studies. Before the cosmological simulation era, there are many dedicated simulations that targets to make the individual clusters and to see what's going on there. But nowadays, in the observation, there are many large-scale surveys that provide a statistically large size of this cluster sample. So we need a similar simulational data set, and the cosmological simulations that cover huge amount of volume can provide that kind of test set. So this movie shows the formation and evolution of the galaxy clusters in the IllustrisTNG 300 megaparsec simulation. They put the dark matter and the buried matter and then try to evolve them to make the systems that we see in observation. And even earlier at the Redshift 3 stage, the large scale structures formed, the filamentary structures can be formed, and in the node of the large scale structures that cross each other, the massive galaxy clusters like these can be formed. So the question we have is are they really similar to what we see in the observation? And I'm trying to answer some of those questions during this talk. The cluster redshift is also a very useful tool to study clusters. Once we have image like this, the photometric image like this, it looks beautiful, and we know that there are some concentration of galaxies. But the real question is, how many of galaxies that we see in the image are really concentrated the same physical space and interact to each other? To know that, we need to know the distance of the individual galaxies, and the redshift surveys can help that mission. Multi-object spectroscopy is very useful because within a one shot, you can get the many redshift within a cluster region. So SNO1 opens this the multi-object spectroscopy era, and then follow-up surveys based on the MMT hectospec, DESI, and the PFS, which will be available soon, are doing the similar task to obtain the multi-object spectroscopy. So the talks, the result that I'm showing to you today in my talk is basically based on the observational data we collect using MMT hectospec, which enables to get the spectra of around the 300 objects in the optical wavelength range. So now, so far, I've discussed 3 ingredients to study galaxy clusters: dark matter, intercluster medium, and the galaxies, and the 2 tools, then the redshift surveys and the cosmological simulation. And then by combining all of these, I tried to explain what I learned so far. Let's start with the spectroscopy observations for clusters. Spectroscopy observations can provide the very rich information of the galaxy systems. First of all, the spectroscopic survey can provide the basis for identifying galaxy clusters by finding the systems that are concentrated in the same physical space. Once we identify the members of the galaxies that are at the same distance from us, from there we can study the galaxy properties and the cluster dynamics and so on. So once we proceed the multi-objective spectroscopic survey for the galaxy cluster members, then we can get this kind of spectroscopic data. And by analyzing this spectroscopic data, we log the galaxy properties in a cluster environment, and by estimating the redshift or the relative motions of the galaxies, we can study the dynamics of the galaxies in the cluster environment. I apologize to the people who already saw this movie before, but I think it's a very interesting movie to see. The cluster community has some idea that obtaining the large-scale spectroscopy survey is very expensive. So to do the cluster science, sometimes people say it's enough to use the photometric data. But I strongly against with that idea just because of this movie. So the left image shows one of the cluster in the red mapper cluster category. Red mapper is an algorithm to identify galaxy clusters based on the photometric information of the galaxies. So in a cluster environment, galaxies are usually concentrated on the red sequence in the color magnitude diagram. So what they did was try to identify the sequence of galaxies in the direction of the sky. And as you can see here, it seems like there is a strong concentration of galaxies with similar colors. And based on that, they assume that the galaxies with the similar colors are really the members of the clusters. And then they infer the mass of the clusters by summing the number of possible member galaxies in this field. On the right-hand side, what I'm going to show you is the spectroscopy is from the spectroscopy observation. The central galaxy, the brightest central galaxy, is sitting at the center of this plot. And as time goes by, I will add the spectroscopic, the relative velocity, radial velocity of the individual galaxies in this field with respect to the central galaxy as a function of the projected distance from the central galaxy. So the central galaxy sits here. The next galaxy, which has similar colors, appeared at the similar redshift with the central galaxies. But as you observe more and more, the galaxies with the similar colors appear to have the radial velocity larger than 10,000 km per second from the central galaxies. Which means the galaxies with a similar color with the central galaxies are not actually at the same physical distance from us. So almost half of them are the contamination from the line of sight objects. So if you measure the mass of the clusters by counting the number of member galaxies, then your mass estimate for the cluster is, the uncertainty is 100%, right? So with this kind of data, it is not really straightforward to study galaxy properties or the cluster properties themselves. So because of that, we want to have dense spectroscopic data. For that purpose, we did the survey called the Hectomap redshift survey. Hectomap is a dedicated survey, the redshift survey that covers 55 square degrees of the sky, which has been done over 10 years. This area was covered by the Subaru HSE PFS, Subaru HSE SSP survey. So we have a very high quality of the imaging data as well. So we start by collecting the small spectroscopic data in 2004, and the real survey starts in 2009. For 10 years, we tried to obtain the redshift of the galaxies in this field. We only apply the two simple cut. One is the target galaxies should have color larger than G minus R color, larger than 1. and the galaxies should be brighter than R band 21.3 magnitude. So after a few years, we see all the larger scale structures in the field. And then as we add more and more spectroscopy information, the larger scale structures becomes much more clear. So after 10 years of survey, we could collect around 100,000 spectroscopic redshift. And based on this, what we did was we tried to identify galaxy clusters that shows a strong overdensity in the redshift space. So when we take a look at the HSC images of this identified system, we indeed see the brightest galaxies at the center and the galaxies with the similar colors surrounding the BCG. So once we construct this kind of cluster catalog, we have plenty of data to study the galaxy evolution and the cluster evolution based on the spectroscopic data. And these are the systems that shows the strong concentration of the galaxies in the phase space diagram as well. In addition to the hectomet, we also did some other cluster spectroscopy surveys. MARC is the survey for the massive nearby clusters with the hectospec. There is a survey called the LOBOS, which is the Greek dancing survey for the northern clusters. And for these northern clusters, we did the spectroscopic survey for about 20 clusters. And the HEX omnibus is the largest spectroscopic survey compilation for the galaxy clusters at the redshift lower than 0.3. So by combining these cluster survey data and the hectomap data, we try to investigate the cluster properties. I'd like to introduce MARC survey a little bit more. MARC is the densest redshift survey using the MMT hectospec. So we select the 10 most massive clusters at redshift 0.06 to 0.12. Per each cluster, we have collected more than 3,500 spectroscopic redshift. ABEL 2029 is one of the MARC cluster, and this one contains about 1,200 spectroscopically confirmed members. So this is the second most sampled cluster in the universe after the COMA cluster, which is at the very low redshift. The MARC survey is useful because we didn't apply any color selection. So within the field, brighter than every galaxies, brighter than 20.5 magnitude in R band, we have spectroscopic redshift. So in the line of sight direction, no matter whether galaxies, what colors do they have, no matter what photometric redshift they have, we simply get all the spectroscopic data for these clusters. So this provides a strong basis to study different topics about the clusters. So with this dense spectroscopic data, we conducted many projects, including the quiescent galaxy evolution, coevolution of clusters and the BCGs, and the velocity dispersion functions of deep cluster galaxies. I'll try to explain these two topics later today, very soon. We also study the galaxy clusters as systems. So one topic that I want to explain a little bit more is the idea called the spectral tomography, which will be, which I will introduce at the end of the presentation. The galaxies in the cluster environments have some special characters. The brightest central galaxies, or if you remember your class, extragalactic science class, you probably remember the term the CD galaxies. They are the extended, they are the really massive galaxies that only appeared in the cluster environment. So that's one of the distinctive character of the galaxy population in a cluster environment. And cluster galaxies are thought to be generally red and dead. And those galaxies appear as a very tight sequence in the HR diagram. The red sequence is one of the characters of the galaxies and clusters. And the question, another question about the cluster galaxy population is what is the mass distribution of the galaxies? And how is it different from the lower density environment? And if there is a difference in the mass distribution, there must be some difference in terms of the dark matter distribution within the cluster environment. And can we study those kind of things based on the observational data we have? That is the question that I want to answer. So to understand these two last topics, we need some theoretical guidance. So in the observation, what we can really get is the observed properties of the galaxies, including luminosity or the stellar mass. In the simulation, we can get the additional information, like the dark matter properties of the subhalos that host those galaxies we find in the observational data. So can we connect these two to understand the general mass distribution and the dark matter mass distribution in the cluster environment? That's the motivation that we did this study. So connecting the observables to dark matter has been a very popular project. It's so popular, so Yenting actually wrote a paper in 2004. So this paper shows the luminosity of the central galaxy, the brightest central galaxy of the cluster, as a function of the mass of the cluster. And Yenting showed that there is a very tight relation between those two parameters. So, being said, if you have more massive dark matter halos, the galaxies that form in the dark matter halo would be more massive. But back in 2004, we could use the luminosity information. And now people are using the stellar mass estimates to derive similar relation. So this image shows the galaxy stellar mass to cluster halo mass relation within for the clusters within the cosmos field. And then they showed there is a generally good relation between those two parameters. So once you have more massive dark matter, you have more massive galaxies. Would it hold in the cluster environment? That's the kind of question we want to answer. However, my argument is that the deriving luminosity and stellar mass is not really straightforward in both observations and the simulation. And this image actually demonstrates my argument quite well, in my opinion. So this one is the image from the JWST. As you can see here, the galaxies are overlapped in a high-density environment of cluster. So let's assume that you have a task to derive the luminosity of these four galaxies from this image. Does it look straightforward? No. You automatically assume that there are four independent galaxies. But it is extremely hard to separate the luminosity from these four galaxies. So measuring luminosity or getting the photometry of these galaxies in observation is not straightforward. And it becomes more miserable when you go to the higher density environment like the galaxy clusters. So luminosity is not a really good proxy to connect the observable properties and the underlying dark matter properties, although Yenting showed a very nice relation. Stellar mass also is not straightforward. Measuring stellar mass is also not straightforward. First of all, stellar mass estimation is based on the photometry. So once you mess up with your photometry, then measuring stellar mass is not straightforward. And also, to convert your photometry to the stellar mass, you need to have a lot of different assumptions, including the slope of the IMF, metallicity of the gas, or the star formation history of the galaxies, and so on. So it becomes a very complicated. Another problem is that it is not easy to get the meaning of the stellar mass in the theory as well. This plot shows the x-axis of this plot shows the halo mass, the dark matter plus everything mass, and the y-axis shows the stellar mass ratio, the stellar mass of the galaxy in that particular halo, and divide by the total halo mass. And both observation and simulation show this kind of relation. And in this, let's take a look at this part. This part, the stellar mass to halo mass relation decreases as a function of halo mass, which means although you have more massive dark matter halos, the stellar mass increment is not really proportional to the increment of the halo mass, which means there must be some additional feature that suppresses the star formation in the high mass region. To explain that, the age-and feedback has been introduced. But age-and feedback, there are many people who study this issue, but it is unclear how the age-and really affects or suppress the star formation within the entire galaxy. So, because of that kind of complexity, measuring stellar mass requires some additional assumptions about the more complicated baryon physics, like the age and feedback. So, because of these reasons, I thought luminosity or the stellar mass has been widely used to connect the observable and the dark matter properties, but may not be the perfect the observable to do that kind of job. Now, what can we do? Since I'm working on the massive spectroscopy, we thought maybe some spectroscopic measurement can be useful. And the idea was using the velocity dispersion. Here, the velocity dispersion I meant is the stellar velocity dispersion of the galaxies. So in the observation, measuring stellar velocity dispersion is relatively straightforward. What you need to do is you need to measure the width of the lines. So how much of the broadening happens because of the internal dynamics of the stars. That's what we measure. Here, what I'm showing is the dark matter velocity dispersion and the stellar velocity dispersion from observations and simulation. In simulation, what we did was we simply calculated the stellar velocity dispersions and the velocity dispersion of the dark matter particles. They seem to have very nice correlation between those two. In the observation here, what we did was we beamed the galaxies depending on their stellar velocity dispersion, and then we derived the galaxy-galaxy weak lensing. And from there, we derived the best fit velocity dispersion when we assumed the simple isothermal sphere. And then that velocity dispersion probably corresponds to the total velocity dispersion of the dark mass of halos, and they seem to follow this nice relation. So these two tests assures us once you measure the stellar velocity dispersion, that is corresponding to the dark matter velocity dispersion, which might be correlated with the dark matter mass. In other words, once you measure the stellar velocity dispersion, you have dark matter halo mass proxies. And one thing that I need to emphasize is that in the simulation, what we have to do to measure the velocity dispersion should be consistent with what we do in the observations. When you go to the simulation, you see the simulation team measure the velocity dispersion for you. But in often cases, they are not really directly comparable with the observational measurement of the velocity dispersion. So what we do in the observation is, let's say there's a galaxy here, you put the fiber that covers certain area of the galaxies, and then you measure the broadening line of sight, due to the line of sight motion of the stars. That's what we get in the observation. So in the simulation, if we want to derive the similar velocity dispersion to compare with the observation, we have to do the same. So in the simulation box, if there is a galaxy, we put some fibers that penetrates the center of the galaxies, and then we need to derive the velocity dispersion to make the fair comparison with the observation. So we did that test, especially for the central galaxies of the galaxy clusters. So here what I'm showing is the velocity dispersion of the cluster galaxies as a proxy of the cluster mass. And the y-axis shows the stellar velocity dispersion of the central galaxies divided by the cluster velocity dispersion. This is very similar to what we saw before in the stellar mass to halo mass versus halo mass relation. These are from the hectomap clusters. They seem to follow very nice relation. Independently, we derive the same thing from the hex omnibus data, and then they seem to follow very nice tight relation like this. So this is the simple relation we derive from these observed sample. Once we get this, what we did was we tried to make this, we tried to compare with the numerical simulation. We found two simulations that provide the theoretical guidance for this relation. And these purple lines show the simulational projection on this relation. They expect the horizontal, the constant ratio between BCG velocity dispersion and the cluster velocity dispersion, which is very weird. And they don't seem to match with the observation. Okay? So we tried to get some help from the simulation people, but we couldn't. And then at the time, the TNG became available, so we did it by ourselves. And then this red squares shows the relation from the TNG clusters. They seem to match better with the observational data. At least they are not constant as other simulations suggested, right? So this is what we got from the TNG simulation. It's not perfect because in the simulation there are more systems with the velocity dispersion of the BCGs seems to be much lower than what we found in the observation. But this is what we got from the most recent cosmological simulation. When you saw this plot, you may find that the slope of this relation looks different depending on the location of the galaxy clusters. And this is our interpretation. In the massive region, BCG velocity dispersion doesn't grow very much as we expect. And that's quite consistent with the picture that these massive galaxies are growing based on through the minor modules. That doesn't add up a lot of mass, but it makes the galaxies bigger. So in this region, the BCGs don't experience that much major modules, and then that's why they follow the same relation, and then they evolve from here to there, following this tight relation. While the BCGs or BGGs at the lower mass system, because the galaxies in that environment can experience major mergers, and they grow very steeply compared to what we see in the high massive system. So that was the interpretation we had back then. But we don't know whether this is the perfect picture to explain the growth of the BCGs and the cluster altogether. The good thing about the simulation is that we can trace back how they look like in the higher redshift environment. So here I'm showing a very simple plot. The x-axis shows the mass of the cluster, and the y-axis shows the velocity dispersion of the BCGs. At redshift 2, BCGs and clusters seem to have similar velocity dispersion. So at this stage, it is really hard to distinguish between BCG and the cluster. But at the low redshift, cluster velocity dispersion is a lot larger than the BCG stellar velocity dispersion, which means at the early stage of the cluster formation, the halos of the BCGs and cluster are not really separated very well. But somehow, as they evolve, the BCG growth becomes very, very slow, while the cluster halos can grow very fast. So this is the theoretical prediction about the structure, the coevolution of the BCG and the cluster halo. Is it real? We need more data to test this relation at the higher redshift. And I think it's a very straightforward test once you have the dense spectroscopy that cover this redshift range. Then I'll move on to the velocity dispersion functions, which is very similar to the luminosity or the stellar mass function. So luminosity functions, stellar mass functions are widely used to guess the underlying dark matter subhalo distribution within the cluster environment or in the general field environment. So because of the reason why I explained why the velocity dispersion would be better than this luminosity and stellar mass, we try to do the same job. And yeah, so for the Abel 2029 and COMA clusters, we derive this kind of velocity dispersion function. And then we try to make the comparison with the field dispersion function. So this white square shows the dispersion function we derive from the field population. And this is the comparison between field and COMA Abel 2029 clusters. One thing you notice is the axis in this area. You don't see a big difference at the low dispersion range, but you see that this at the axis in the cluster environment. This axis is not surprising because, as I described, the massive galaxies, central galaxies, are usually appearing in the very dense environment. So this is consistent with what we know, what we already know about the clusters. But the funny thing is, these axes is not due to the single BCG. There are some additional galaxies that appear, that contribute to the axis of the axis in the cluster environment. So we wanted to understand what we got, the velocity dispersion function can be really useful can be really used for tracing the underlying dark matter halo mass distribution. To do that, we wanted to derive the similar properties from the simulation. And here's the result for the comparison. So here what we did was we simply derived the velocity dispersion function from the IllustrisTNG simulation. We select the three most massive clusters in that simulation, and then we derived the velocity dispersion with the same manner with the observation. And then they appeared like this colored line. And these two green points are the observed velocity dispersion function. There's something wrong. Simulation predicts very different velocity dispersion function. And my ambitious plan was, okay, once they match in the stellar velocity dispersion, then we can translate that into the dark matter and halo mass. So we can, once we measure the velocity dispersion function for anywhere in the field, then we would get some idea about the dark matter halo distribution. But that plan was broken from the beginning because the simulation doesn't predict the same shape of the velocity dispersion function in the stellar component. Why is it? We first check the number of subhalos in the cluster environment. The white crosses shows the member galaxies with the mass, stellar mass larger than 10 to the 10 solar masses. Cyan circle shows the similar stellar mass of members within the TNG simulation. Generally, TNG predicts about 10 to 20% lower number of member galaxies in their clusters. Okay, but this cannot explain this difference. This is factor of 10 difference, right? 20% is not enough. Then we derive this stellar mass to velocity dispersion relation. The red dashed line shows the relation we derive from the small galaxies, and the contour shows the distribution of the galaxies in the TNG 300 simulation. The yellow square shows the median of the galaxies. Then you can see that there is a discrepancy in the m sigma relation. So just at the given stellar mass, simulation predicts a lot smaller stellar velocity dispersion that propagates to the difference in the dispersion function shape. Right? So the TNG simulation tuned the TNG team tuned their simulation to explain the stellar mass distribution with the observed sample. But they didn't tune anything else, and there it becomes a problem. They can explain one physical parameter, but they fail to explain the other parameters, like the velocity dispersion. And you can imagine that the velocity dispersion, it should be quite insensitive to the very complicated baryonic physics recipes they implemented in their simulation, because it's a simple gravitational parameters. And we are pretty sure that we understand the gravity pretty well. But they failed to explain the velocity dispersion in their simulation. We try to understand what makes the simulation wrong about this. First idea was maybe the resolution of the simulation is not good enough, because TNG 300 individual stellar particle has a mass of about 10 to the 5 to 10 to the 6 solar masses, which corresponds to the mass of globular clusters, not the individual stars. So if that's the case, maybe they did something wrong. I mean, there must be some limitation what they can do with that kind of mass resolution simulation. Indeed, there's some hint. The TNG 50 simulation, which has a much better mass resolution, the same m sigma relation appears to match better the observed relation. But there's no big difference between TNG 100 and TNG 300 simulation. So this is something that we need to understand better, what is the impact of the mass resolution of the simulation. There are other quantities of the simulation that we need to consider, like the box size or the baryonic physics that they implemented in the simulation. We did a simple test using the Eagle simulation. This is work done by my students, Jung and Choi. So here, this velocity dispersion function is based on the Eagle simulation with the zero agent feedback. So we asked the question whether if we implemented the agent feedback or not, would they affect the shape of the dispersion function? And then, indeed, they affect the shape of the dispersion function. But without AGN, agent feedback, that can explain a little bit better the stellar mass to velocity dispersion relation. But the shape of the dispersion function looks totally different from what we have in the observation. So this may not be the real case of the simulation. Another idea I got from my colleague is that the simulation box size of the TNG 300 is too small to trace all these the galaxy internal dynamics. So we use the simulation called Horizon Run 5, which covers a lot bigger volume than the TNG 300. And then this orange circle shows the relation, m sigma relation, for the galaxies in the HR5 simulation, and they seem to match better with the observed relation. So maybe box size plus mass resolution effect are the source of the discrepancy in the m sigma relation. So final remarks on these studies. is that stellar velocity dispersion shows some good correlation with the underlying mass distribution, both stellar mass and the velocity dispersion. But the 0 point of the relation is totally wrong. And we don't know yet what causes that kind of discrepancy. Because I don't have enough time, I'll just skip more about this. The last two topics that I want to cover is the how to study galaxy clusters with the dense spectroscopy. The one project I did with my colleague was to estimate the mass accretion of the galaxy clusters. So once we get this kind of dense spectroscopic data, we can select the galaxies within a certain distance from the cluster environment. And then we can estimate how much of mass will be accreted by the cluster in the predicted time. So that's what we call the mass accretion rate. So in the theoretical, like embodied simulation or the cosmological simulation, we can calculate the mass growth of the galaxy clusters. Then the question we had was, can we constrain that with the observational data as well? So we asked that question. So we select this info region, and we assume that the mass of this info region will be accreted by the cluster within the 1 gigayear timescale, and then try to compare with the theoretical prediction. It seems to match very well. The circles shows the prediction from the embodied simulations, and the other symbols are the mass accretion rate we measured from the observed sample. And they seem to match very well with the mass accretion rate prediction from the embodied simulation. And then we also calculate the mass accretion rate as a function of redshift, and these colored circles shows the mass accretion rate we derived from the hectomap cluster sample. And they seem to well located within the theoretical prediction we showed in the cyan symbols. So once you have this kind of dense spectroscopic data, we can also provide some constraint in the mass growth of the cluster as well. Okay, this is the final topic that I want to introduce. I see some big lensing experts in the room, so I don't need to explain very much detail about the lensing. So to be short, once we have the mass concentration, like the galaxy cluster, the mass concentration can distort the image of the background galaxies. The big lensing analysis is by measuring the distortion for the statistically large sample and try to reconstruct the mass distribution between the lensed galaxies and the observers. So that's the idea of the big lensing analysis. And because the galaxy cluster is such a massive structure, which can distort the image of the background galaxies very well, we use the cluster as a lens in many applications. And also, by reconstructing the lensing, the mass distribution, we can also constrain the mass of the galaxy clusters as well. So if you are interested in the cluster cosmology, for example, by having this kind of mass estimates, you can construct a better cluster mass function, which can be an independent tool for the cosmological parameters. And this is a work done by Kai-Feng Shen, who's now at MIT, but who used to be here. He included the lensing map of the hectomap region, where we have the dense spectroscopic survey. And then he identified the several peaks that must be corresponding to the massive clusters. So the idea we had was, okay, once we have this kind of high resolution photometric imaging that enables the weak lensing analysis, can we do a better job by combining the lensing and the spectroscopic data? So that's the idea. There are several big contributors on the lensing analysis. First is the intrinsic shape of the background lensed galaxies. So, roughly speaking, bear with me, Keiichi. Let's say there is a circularly looking galaxies. And if we measure the galaxy ellipticities from the image, then we can assume that that elongation happens due to the gravitational lensing of the massive cluster. But the real question is, do we really know that the background galaxies are really circularly shaped? We don't know. So that describes the intrinsic shape problem. And that's one of the biggest source of the lensing analysis. The second biggest source, in my opinion, is the redshift distribution of the background sources. So let's say this camera is a lens. And then I try to get the elongation of your images by the lens. The amount of elongation or the distortion is depending on the distance between me and the lens and the observed galaxies. However, in the lensing analysis, because they have to use such a large number of galaxies, they don't have the very precise distance measurement. So they use the color, or they use the photometric redshift, or they simply assume that all galaxies are at certain redshift. And that contributes to the uncertainties in the lensing analysis. So our idea was, for the Mach clusters, for example, because we collect the spectroscopic data for all galaxies brighter than certain magnitude, many of them are presumably the background galaxies that would experience the dispersion by the lensing of the galaxy cluster. So what if we do the lensing analysis based only on the spectroscopically confirmed background galaxies? Can we do a better job in the lensing analysis? That was the idea. And because we combine the weak lensing and the spectroscopy, that's what we call the spectroscopic weak lensing tomography. Okay? And here's the result. Here in this plot, what I'm showing is the distortion along the tangential direction with respect to the cluster center, and the cross direction. For the background, spectroscopically confirmed background galaxies. If there was no signal for these galaxies, both distributions should be randomly appeared. But we see the preferential excess of the tangential ellipticities. It means the spectroscopically confirmed background galaxies are aligned in the tangential direction as we expect in the general lensing analysis. And then we compare, we derive the differences between those two histograms. And this yellow dashed line is not a fit to the data. It's the model prediction based on the lensing analysis. So here, what we did was, let's assume that there is a Abel 2029 light mass at the redshift. And then what happened to the background galaxies? Then, so this yellow dashed line is purely model prediction. And they seem to perfectly match with the observed sample, which means that we can do the weak lensing analysis based only on the spectroscopically confirmed background galaxies. And the level of significance is about 4 sigma, which is comparable with the very first lensing, weak lensing estimate based on the photometric galaxies. And this plot shows the mean ellipticity of the galaxies as a function of redshift. At the zero redshift, because they should not experience any gravitational lensing, they should appear close to the zero. And the background galaxies, depending on their distance, their distortion should be appeared because of the lensing. And here again, the white line shows the model prediction by assuming the mass of the 2029 mass. And then they seem to appear quite well matched with the observed sample. So based on this, we are pretty sure now that we can do the lensing analysis based on the tomography. This is the simulational result. So once we assume that we obtain the PFS light survey for the massive clusters, then how can we do better this job? Indeed, we can do a very good job with this amount of error bars. So that's what we want to do with the future spectroscopic data. And these will be very useful tools for the future cosmology because of three reasons. First, by doing the lensing analysis based on the spectroscopically confirmed galaxies, we can estimate the weak lensing mass without significant uncertainties. Or, if we can match this model line, we can derive the cluster mass totally independently. So that's the second application. And this model curve, the shape, depends on the cosmological parameters because this is all related to the angular diameter distance. Then we can use this as a totally independent cosmological tool. I think I overspent my time, so I'll stop here with my summary. Thank you very much for your attention.
Okay, questions for Jubee? Thank you for the nice talk. So for the comparison of the observation with IllustrisTNG simulation, the discrepancy in this velocity dispersion function is very surprising.
Yes.
While actually you are finding good agreement for this comparison between BCC to the cluster dispersion relation.
Right.
So you didn't conclude, but do you identify the cause or?
Not really. So this plot actually had some hint about it. The BCG velocity dispersion somehow match in a massive range. So these are BCGs and these are BCGs. So when we took a look, the most massive part apparently seemed to match pretty well in the observation and the simulation. But for the low mass population, it becomes problematic. There could be several reasons why. First of all, defining the BCGs in the simulation is not straightforward from the beginning. What they do is they apply the friend of friends like algorithm or subfind algorithm, and then they subtract the components that are belonging to the member galaxies. And the remaining part is considered as the cluster plus BCG population. So in this case, maybe the contamination of the particles that are really belonging to the entire cluster halo, not the BCG subhalo, can affect the velocity dispersion measurement. But there we didn't do anything to treat the component. Because in the real observation, if there are stellar particles in the line of sight direction, they shouldn't affect, they should not be discarded in the observation as well.
Because of the optimization of the feedback models, do you can reproduce this stellar mass function instead better?
Right. The two things. So first of all, stellar mass function seem to be matched pretty well with the observation, but they tune their simulation to match that. So we don't know how much tuning they really applied in their simulation.
Like, compared to the, other simulation like Bahamas, they give more Asian feedback.
Right. So apparently, only one test we did was based on the Eagle simulation, but from that comparison, without Asian feedback, both stellar mass function and this velocity dispersion function shape don't match with the observation. So, for example, this one is from the no Asian feedback model from the Eagle simulation. The equivalent stellar mass function for this simulation looks totally different from what we have in the observation. So my current conclusion is that we need the Asian feedback to explain the mass and the velocity dispersion function shape, but there's still way to go to calibrate the velocity dispersion measurement.
Yeah, I mean, so I'm very interested in the comparison between remapper and the heteromac cluster, and there's a discrepancy in the richness. And I'm curious that how often do you see such a discrepancy? And imagine that's simply just a two cluster along the line of time. That's
Right.
how often in your heteromac view.
Yeah. So although I showed you extreme example that shows the double cluster, in my opinion, RedMapper did quite good job. So in our 2018 paper, we showed that the true member fraction, depending on the membership probability calculated by the RedMapper algorithm. There is a contamination about 20 to 30% in total, but they do a pretty good job. So more than 90% of the RedMapper clusters in the hectomap regions seem to be the real clusters in the spectroscopic data. But one thing that I need to emphasize is that they didn't identify all the galaxy clusters we could identify with the spectroscopic data. So their completeness seems to be high, but their purity seems to be low. That's, yeah.
So if you can follow up, if you can rederive your correct richness from the heteromac, and you can simply plot the heteromac richness versus max, and how wrong is the remapper base richness?
So there, I think 20 to 30% in total. Yeah. So we did that test twice. One with the hectomap sample. Second with the hex RedMapper sample. So if you look at the Rhines et al.'s paper, we did the same test. Rhines et al. Sample is slightly better because they cover the wide range of the RedMapper richness. In hectomap region, there are not many clusters with the high RedMapper richness. So for the certain cases, we don't have like a very concordant observational evidence, I would say. Roger?
Can you return back to the slide and compare the cluster velocity dispersion with the stellar velocity dispersion? Yeah, that next one. Yeah. I'm curious, if you look at the higher end of cluster velocity dispersion, essentially the red, orange points are below the line we traced. I mean,
so this line doesn't really mean a lot because it's a simple the fit to the median of the distribution. Yeah. But the point that I wanted to make is that surprisingly, clusters and the BCGs know which stage they are. Otherwise, they have to like evolve like, crazily in this plot. But they are concentrated in the very narrow region in this plot. So the BCG growth must be restricted by the cluster mass somehow. That's the kind of implication of this plot. And then my thought was in a large velocity dispersion systems, because galaxies are passing by each other with a very high relative speed, so the major merger kind of thing cannot happen that often in the massive system.
But you are thinking only about the BCG evolution, but the cluster itself evolves to mergers.
Right. So by creating the material through the filamentary structures, cluster can grow quite, with a fair fraction, while the BCG at the center, because the nearby galaxies are passing by with a very high speed, so the actual merger doesn't really happen for the BCGs. That's the picture that I have.
Great. I think it's a good time to close, but we can continue the discussion outside. There should be tea and refreshments. And there is still one spot available for dinner with Jubee. So if you're interested in joining, please let me know. That's it. Thanks, Jubee.